Hello everyone. Today we will be talking about fast convergence and the effect from design point of view when we have fast converged network, when we especially tune some timers, etc. This will be another service provider network discussion, and we will talk not only fast convergence but other things as well from design aspect. Mainly fast convergence we want to focus on. And my name is Orhan Ergun. With me, Mohamed Radwan here. And welcome, Mohamed.
Hi, Orhan. Nice to have a second session with you.
It's nice to have you too. So let's jump in. What we will talk. Let's basically clarify.
Yeah. So today we'll talk about another service provider project, and maybe in the future we can cover some enterprises to make sure that we fulfill the needs for multiple audience. So as you can see, as you will know, that fast convergence is becoming one of the main pillars of each service provider project. So that's why for me, fast convergence I did it many times since I started. And each and every service provider, either it's a green field or it's doing some enhancement, usually they consider fast convergence as one of the main services they want to make sure it's working as perfectly. So here, as you can see, the main challenges is that we have fast conversion for a service provider. It was supporting mobile, as you can see. So it has some RAM and 3G, 4G terminated into some of the aggregation routers. And in addition to that, it serves some customers, some business customers like, again, layer 3, and provide internet services for the mobile and the fixed broadband. So we provide the internet for MBB and FBB. Another point that we have multiple vendors. So as example, for the service layer, we had some F5 working as a CGNet and load balancer. We have some checkpoints, firewalls, okay?
Okay.
And even for these
at this moment,
PEs, not all of them were Cisco, so we have multiple vendors. We have Cisco and Juniper. So once we started the journey, we would see how we thought about the design and what were some of the challenges we considered for this big service provider.
Can you hear me, Mohamed?
Yeah,
okay.
Yeah, I can now.
Let me clarify a couple points so far. RAN stands for Radio Access Network, MBB Mobile Broadband, FBB Fixed Broadband, CGNet, Service Layer CGNet it says, CGNet Carrier Grade NAT. Some of you might know as LSN, Large Scale NAT, and these are the terminology, DC of course, data center, etc. So we are moving. Also what we are seeing, aggregation network, generally service providers like we call access network, then aggregation. Sometimes depends on the scale, we might have pre-aggregation, so aggregation after aggregation, core network. For the core you might hear as backbone, etc. So this is what we are talking at the moment, guys. Let's continue, Mohamed.
Exactly. So as you can see here in this service provider, they have multiple services. So they have mobile, they have internet, they have some business customers, and they have also video. In addition, that also they have the normal network control, network management, and they serve their retail office retail stores, because they are mobile operators. So also they want to serve their retail, provide them access to their data center, and provide them access to the internet. So they have a lot of services. Each of these services come with its own requirement. As we are aware that mainly for voice, which include voice, real time, and mobile, that we need to make sure that, for example, the delay is 150 milliseconds. So in case of failure, they were looking for trying to reconverge in sub 200 milliseconds. And for other services, as example, like video, they set a limit that we need to converge under 1 second, okay, as a convergence. For internet, it was mainly best effort, so we didn't have a solid KPI or SLA to meet for this service provider. So that's why when we start thinking about a solution to meet this, we try to think about all the layers which we need to address. One sec. I'll come back again to this slide, but can you see this next slide?
Yes.
So yeah, when I start thinking about how to make sure that to meet this SLA and converge under sub-second, I start thinking about I need to make sure that the convergence is happening into these multiple layers, because sometimes these layers depend on each other. So as we all know, as example, usually the IGP will converge after detecting a failure from the physical layer. Then based on that, BGP will converge, and then the application using BGP will converge after the BGP is converging. So when we start thinking about this convergence, we need to consider the relation between the multiple layers. Okay, 1 second, please.
So while you are arranging, let me clarify a couple points. For the voice, 150 millisecond, Mohamed said, general accepted best practice for the voice, 150 millisecond one-way latency, not RTT. And for that one-way, you may not remember was it one-way, two ways, etc. Just maybe remember, we also call it because mouth-to-ear latency. Mouth-to-ear latency for voice, 150 millisecond. And for this network, from the customer, what Mohamed said from the customer, the requirement for the video traffic was less than 1 second convergence time. Since we are going to talk about fast convergence, so we need to know the parameters, numbers here for the applications, critical applications, their services, in fact, like as we said, mobile service, internet there, business, VPNs, etc. Video, is it IPTV plus something, or what type of video?
It was mainly IPTV. There was no video on demand. It was mainly IPTV. So it's streaming. That's why the limit wasn't high.
Okay.
Yeah. So yeah, as you mentioned, so now the pin is working. So once we start thinking about the design itself, I will show you what we did in each layer. But what I need you to make sure that these layers are related somehow. So what happened in one layer actually affect the second one. So that's why you need to make sure how fast you are in convergence, and maybe for some protocols, they need to wait for other protocols to converge before sending the traffic. So as example, usually for IGP, you need to wait for BGP before sending this label. Another point, a very important point I want to highlight is what are the steps to converge? So let's say, I want to get rid of this.
Maybe we can clean also this.
Yeah. I'll clean the screen and come back.
Meanwhile, let me talk something then. So we will be showing now convergence steps. Usually we mention about 4 steps. So those are, the first one should be detection of the failure. Failure can be link failure, node failures, or device routers, etc. failure. SRLG failure, shared risk link group, we call it, right? So different type of failure might happen. Local failure or also remote failure might be. But we will be generally talking, when we talk about fast convergence or fast reroute, there are differences. I will mention also about those differences in this recording. So detection is the first step. And we will be talking about different mechanisms for detecting the failure, different type of failure. BFD, of course, will be just one of them. BFD, people are thinking that it is the convergence mechanism. No, BFD is just one of the steps in overall convergence. So BFD stands for bidirectional forwarding detection, fast failure mechanism. So fast failure detection mechanism, sorry. And then after that, we will see propagation. When there is a failure, the local node attached to the failure needs to inform its neighbor, and entire network needs to be informed. And after that, when the device receives this new information, they need to find an alternate path, and this alternate path needs to be signaled into the ribbon FIP. Update is basically control and data plane update. Now, Mohamed will mention these steps and we will deep dive. By the way, which IGP we have in this network?
We have ISIS.
Okay.
We have ISIS here in the network. So yeah, let me repeat again. So yes, thank you, Orhan. So this is very important and for your life, and when you design fast convergence, you need to be aware of these 4 steps, and you need to find the right tool to enhance each of these steps. So let's say if let's say a failure happened here on this second T0, the failure happened. So I need some time to detect the failure. It will take me to T1. Then I need to inform my neighbor I have this failure. After that, I need to find or process an event, which means I need to find an alternate route or alternate path, which will then I will finish by T3. And finally, I need to update my routing information base and forwarding information base with this new path. So this will end up in T4. So let's say for the old days, if maybe the detection take 3 seconds, and then the propagation take maybe 10 seconds, and finding an alternate route take us up to 5 seconds, and finally updating is 1 second. So this means for me, after detecting the failure, it took me around 19 seconds to converge. So for the old days, I remember in the late 90s and early 2000s, this was very acceptable, especially in IP network, where we mainly used for campus, mainly used for data and internet. So this was very adequate and sufficient. But with the converged network, because as you remember, we have mobile calls, we have video, we have very important business customers. So in this case, we need to converge in less than a second. So in order to converge in less than a second, I need to make sure that these 4 times will be as fast as possible.
Okay. Mohamed, so, this 19 seconds is not the real time, right? We are just making up numbers.
No, just like an example. Just an example. Yeah, just giving them, just to make it easy to do the math.
Yeah, okay, but the propagation delay for the propagation, you said 10 seconds would be too much, by the way, for real life. Even probably back in old days. 10 seconds. So here for 2 timers generally today are high compared to others. Detection time can take a lot of time if you are not utilizing some special mechanisms like physical layer down detection or BFT, etc. And update. So update, fib update, control data plane update for the new information. Otherwise, propagation generally depends on a couple parameters. One is serialization latency, what is your link capacity. Another is distance, physical distance, propagation latency we call it. And every 1,000 kilometers at 5 milliseconds there. So, and step 3, by the way, if you are running ISAS, in this network we are running ISAS, if it could be OSPF as well, it is SPF. SPF will run and will find an alternate path for us. Let's continue.
Yeah, but just to highlight some point here, Orhan, when we talk about the propagation step number 2, I don't mean the time it will take to send the packet on the wire, to put the packet on the wire and to reach the neighbor. From some old routers, as example, to make the network stable, if the router detects a failure here in this T1, some of the devices used to have something like a backup algorithm that I will wait. Maybe this link has been flapping, so I will not inform my neighbor directly about the failure. Maybe I will wait 1 second, 500 milliseconds, and so on. Then I will send an LSA or LSP in case of ISS, informing my neighbor that there was a failure. So that's what I meant about this propagation of the event. You need to be how. Then we can have this trade-off. Shall I send it immediately after I see it, or shall I implement something like a throttling algorithm to make sure the network is stable? Not whenever I see each failure, I will send it directly, but maybe for the first one, I will be very fast, but then I will start doing some backoff for the next one.
This backoff, by the way, the Mohamed mentioned, is also in other protocols like OSPF as well, and we call it exponential backoff. So basically, it's similar to IP event dampening mechanisms or BGP. Basically, when I see the first packet, I will generate the update as soon as possible if it's not zero, and then if there is flap or somehow brownout in the network, so I will postpone the subsequent SPF runs. So I will not run immediately SPF again. Maybe there is a flap in the network, so I don't want to consume more device resources. Yeah, excellent.
Exactly. Yeah, great. Thank you, Bob. So let's say, so these are the 4 steps. Let's go to the next slide and see for each step what we have done so far.
Yeah.
Let me erase all drawings. Okay. So here, can you see my screen now?
Yes, but still the convergence steps slide I'm seeing.
Oh, really?
Yeah.
You don't see the table?
Not yet. Not. I think it's coming. At the moment, blank. Yes, it just came, but I'm now gone. Yes.
Okay now?
Yes.
Okay. So let's see. Remember this layer we talked about that we try to enhance. So I will try to categorize what we have done into layers, and then we take about each of these features. Is it fall under detection or propagation or so on? For physical layer, which also apply to the ISIS, because when we detect the physical, we detect it into the IGP. So usually we have a couple of things to do here. So from detection perspective, this is something we inherited from the old days, from SDH and ATM. We used to have, if you have maybe 2 ATM switches or 2 DWDM boxes, and there's a link between them, and maybe your device is connected as IP here, directly or point to point. So we have what we call it carrier delay, which carry your signal, like a wavelengths and so on. So when a device, when a port here detect a failure on the link, usually we had to configure this carrier delay that once you detect this failure, don't send this notification to the upper layer immediately, but just wait maybe for, at that time it was very common to wait for 2 seconds in the physical layer before informing the IGP that I have a failure into my optical or electrical, mainly optical links. So this was not acceptable anymore, and in most of the new implementation, everybody is recommending to set this carrier delay at 0, especially in the downtime. So carrier delay will have 2 notifications. When the links goes down, it will raise a notification, and when the link come back up, it will also tell another notification to the upper layer. So in this project, what we decided to do, when the link failed, I need to inform ISIS immediately about the failure. So that's why I will make the carrier delay 0 milliseconds. I will not wait at all. But when the links come back up, I just need to wait a bit to make sure it's not flapping, to make sure that everything is okay. And because when the failure happened, I already have a backup route, so no need to be hurry and inform the upper layer about the up state immediately. So that's why we decided to put it as 10 seconds. Another important tool which we use for detection, which is BFD, which would be very important in case if I have, as example, a switch in the middle between my 2 routers, so they don't have a direct notification if a link failure into the remote side. So you can configure this BFD session between these 2 neighbors. And BFD is a very light protocol, and as I mentioned, for our case, we have some core devices as a Cisco, and some of the PEs were Juniper. So in this case, depend on the device, depend on the hardware, and the iOS version. You need to agree with the interoperability testing and to make sure you're not putting something not supported by the other vendor. So in this case, we decided within the core, we will have DFD configured as 100 milliseconds per keep alive, and after 3 failed failures, it was 100 milliseconds in the core and 300 milliseconds on the edge. Okay, and the last point that when we have an interface failure, we will implement something like dampening. Like whenever each failure will happen, I will have a penalty. And then if failure happen again, I will have a penalty. Then we will wait some time to reuse this interface. But we decided not to use this feature into BGP because now it's, as we know, is not something good practice to have dampening for BGP.
Let me make it clear basically for the audience later on. They might think why they are saying this. In fact, there are some work also done, some real life testing by RIPE, and one of my articles you can find on that, I am mentioning which actually RIPE paper is defining this. If you type Orhan Ergun BGP pet hunting, so BGP pet hunting, basically the convergence process of BGP, and pet hunting is the behavior of generally pet vector protocol and distance vector protocol like EBGP as well. You need to hunt the pet when there is a failure. We need to basically go through this process. And when we do the event dampening for BGP, the possible problem for penalized prefix can be too much than your expectation. So what I'm saying, you might be expecting this prefix to be penalized in, let's say, 1 minute. But suddenly, because of pet hunting process of BGP, you might see 30 minutes of this prefix to disappear from the global internet, for example, default free zone, DFZ. So which means, let's say you are penalizing and you don't advertise to your upstream some prefix to BGP dampening. You said, I will not send this prefix to my upstream for 1 minute if five times if I see this prefix flapping. But then suddenly you are removing this prefix from global routing table maybe 30 minutes. As I said, there are some real life work on that done by RIPE, and their recommendation also I am sharing in the article. If you check Orhan Ergun BGP pet hunting on Google, you will find a link for that. So for the so far what I understand, what you did is both carrier delay and the BFD on the same interfaces you enabled, Mohamed, correct?
Yeah. Okay. Let me go back to the drawing again. As you can see, here we have multiple layers. So, here it is.
NPE, UPE, by the way, also we are seeing it in left. P stands for provider, NPE, network PE, UPE, user PE. NPE generally will connect the network devices, our infrastructure devices, and user termination, like business customer, for example, is terminated on the UPE guys in service provider networks. Okay.
Yeah, so as I mentioned, here you have multiple layers. So DFD timers was configured differently depending on the support of the other devices. So as I mentioned, inside the core, because it was supporting DFD, so we went very aggressive. In some places, we went to 15 milliseconds as a keep alive, so we converted 45 milliseconds. In other places, we depended on a server, we put it at 100 milliseconds if the device supports. When we are peering with the service layer, as you know that maybe the F5 was doing the CGNet and then sending the traffic back to the internet gateway, okay, and send it to the internet. So we have a BGP session between the router, the aggregation router, which is receiving the internet traffic from the user, and the F5, which will take this traffic and do the carrier grade NAT and then send it to the internet gateway. So the F5, in order to do that, we have this BGP session. So, and we need to make sure that the BGP will converge as fast as possible. So we have to enable this DFD and to support it only as 3 milliseconds. This also applies to some of the Juniper devices, which was there in the network. Some of them were a bit old devices with an old
3 milliseconds or 3 seconds you mean?
Sorry?
You said 3 milliseconds, you mean 3 seconds, right?
300 milliseconds. So
300 milliseconds, okay.
Yeah. So this was, as I mentioned, what we did for BFD and carrier delay.
Okay, I have a question on this one. You said on the core devices, core interfaces, BFD was 50 milliseconds and 3 keep alive. So was it stable after that?
Yeah, so as I mentioned, it was only between the core and these core devices was able to support that. Some of them was CRS, Cisco CRS, so it was capable of doing that. And for other, where we peering with other devices which is not capable of doing this very aggressive timers, we put it up to 100 milliseconds. Okay.
Okay. In the core, up to 100 milliseconds. At the edge, up to 300 milliseconds.
Yeah. In the core, we have to have two cases. If within the core, all the devices CRS was 15 milliseconds. Between the core and some of the MPE, 100 milliseconds, and toward the edge was 300 milliseconds.
Okay, so far we understand these are BFD, bidirectional forwarding detection, which is used for fast failure detection, BFD timers. Okay, guys, not overall end-to-end convergence. For end-to-end convergence, we need those 4 steps. BFD is the first step. So we will understand at the end what was the actual convergence time when there is a core link failure, edge link failure, core node failure, edge node failure, etc.
Exactly.
Okay.
Yeah. So let's go back to the table. Yeah, make it clear. Okay. When it's come to logical, we'll take it quickly because I watched the time. When it's come to logically, there are some recommendations. As example, as you know, the convergence in some protocol, it depends on number of prefixes. That's why summarization will help a lot when we looking for a fast conversion. Another point is bundling. If you have 2 physical interfaces and you want to assure better convergence, instead of having different routing protocol instance running between these 2 devices, it would be better to have it in a bundle. So if I have router 1 and router 2, and for kind of resiliency, I configure these 2, I have 2 links. So instead of configuring each link as a point-to-point and give an IP address here in this link and another subnet here, and if link fails, the second link will take over, it would be better to configure these 2 links as a bundle and put all the logical configuration in the bundle itself. Also, toward the end user, we need to make sure we have HSRP as a global for all the next protocol. We need to make sure that we are supporting. If the device supports non-stop routing, we have to enable it. If it doesn't, we can support non-stop forwarding and global and graceful restart will be with us in both cases. So this was about logical enhancement, which we recommended. When it comes to ISIS, you have 2 options: either to configure fast hello for detection or rely on BFD. So the good thing about BFD, it's a very light protocol running. Some people think it's running on layer 1, layer 2. and then it's update to the upper protocol like ISIS and BGP and even OSPF, and a lot of protocol can utilize this PFD. So in our case, we decided that we will not use fast hellos. ISIS will depend on BFD.
Okay, Mohamed, at this moment, let me ask one question. For non-stop forwarding, non-stop routing, did you also enable NSF, NSR in the core or just edge?
No, in the core as well, for sure.
Why you did on the, especially NSF, non-stop forwarding in the core, you have multiple parallel link, definitely.
Yeah, we enabled the NSR in case of, because, you know, let me go to the drawing again. If you consider if you consider this drawing, actually, we have multiple sites, and each site we have a couple of routers on this site, okay? And most of the PE on the site are connected to these two routers on the site in a square shape, okay? So we wanted to make sure that in case of, and each one of them have multiple RP, okay? So these two devices were working as example. In case of one device fail, the second one and the second RP can take over without affecting the traffic. So within the core, we configure non-stop routing, and we configure it also in the edge.
Yes, non-stop routing, okay, but I am seeing why you had non-stop forwarding, NSF, although you have multiple parallel link.
Yeah, no, I meant, yeah, as I mentioned a couple of minutes ago, if the device support NSR, like in the core, we only configure NSR. If the device doesn't support NSR, we configure NSF.
And this is true for the core as well as edge? You did like that?
As well as edge, yeah.
So basically we have everywhere NSR if the device supports, and NSF is, okay, let's by the way clarify very fast, and before we move on, there are two questions also that let's answer them. So NSF, non-stop forwarding, so if there is a control plane failure, or maybe you are doing some maintenance, etc., forwarding doesn't stop. So, but for this one, basically we have the data plane redundancy, and non-stop routing also in case of, again, generalized CPU problem, etc. You have, let's say, control plane is either you are maybe updating or there is a failure. For each and every routing protocol or any packet, we have, of course, redundant RP, redundant control plane on the same box, and we are synchronizing all the states between the control plane in case of NSR. NSF, you don't have to synchronize the states, etc. So NSR in this design, basically they enabled on core or the edge devices if it supports. If not, non-stop forwarding, generally, because non-stop forwarding in NSF is not recommended much in the core, because in the core of the network we generally have a lot of redundancy. On the access network we have still redundancy most of the time, but the access networks generally ring-based topology. Core either very densely partial mesh or full mesh. The reason access network blast radius is much less than core network, backbone network. What is blast radius? In case of, let's say, problem in the core network, the effect to the service, to customers, will be too much if there is a core backbone failure and problem. But access is not like that. Access is terminating very small number of customer traffic compared to core. That's why blast radius in the access network failure is less. That's why we don't think about the redundancy in the access network not as core network. That's why not much redundancy compared to core network in the access network. That's why. So why always asking why the core excessive redundancy we see, and generally full mesh topologies we see in the core networks on the service providers. but access either ring, but if they have so much money, or critical access sites, let's say, then hub and spoke you might see as well. This is how real life works. And since you don't have much redundancy in the access, NSF we generally recommend there. If NSR capability you have, it seems a lot of good money you have, so NSR can be deployed too. But in the core, NSF is not a good practice to have non-stop forwarding, because anyway you have either ECMP or multiple parallel paths, maybe not ECMP, but you can do maybe UCMP through the traffic engineering, etc. Normally, of course, OSPF, ISS cannot do unequal cost multipath, but we are doing it most of the time with the help of traffic engineering. So far, many RSVP-based traffic engineering, but now we are starting to see segment routing TE as well. And by the way, will be one of another discussion will be based on segment routing with Mohamed. We didn't plan yet the day, but we will be talking about that one as well. Let's continue, Mohamed.
Yeah, thank you, Orhan, for the explanation. There's something very important I want to highlight. Again, when you configure your fast convergence, let's say a lot of people, there is a debate in the field. As example, if I have two devices directly connected with a fiber, so here we have multiple. I saw a question on the chat. If we have carrier delay, why we configure BFD? This is a big argument in the markets. That's why if I have a carrier delay and maybe a DWDM or direct connectivity dark fiber, if a link fails, I will detect it very quickly. So most probably I will detect it less than 50 milliseconds, even if the BFD is configured, as example, with 100 milliseconds. So most of service providers, they configure BFD as extra level of security in case of maybe UDLD, in case of one of the fibers failed, in case of there is something wrong in the control in the specific optics. That's why the link failed, but the optics is not sending this signal to the upper layer. So in most, you configure multiple tools to help you to detect as fast as possible. You don't want to leave it to bad luck or leave it to problem or bugs or so on. So you depend on the loss of signal, which we call it loss in most of the optical links, and the carrier delay. And in 10% or 1% of the cases where maybe carrier delay will be a problem on the optical or the SFP, you rely on BFD. Okay. Another point that's why we have these different tools to use. A very important point, as Orhan mentioned, it depends on your topology and resiliency. You decide which tool you use. As we mentioned, we use NSR here, and maybe we use NSF on the edge. Another point, let's get back to OSPF, on ISIS, and see what other tool which we used.
Yeah.
So here we used also something called prefix priority.
Mohamed,
prefix priority?
I cannot see that slide. I can still see this previous one. You, I think, share at the moment the table. Table is not seen on the screen.
Yeah, 1 second.
Meanwhile, while you are opening that, another question: 150 to 100 millisecond convergence is a standard or not? Usually, service providers are looking for less than 50 milliseconds. They don't look for this. Just let me answer. You can also add your point. So 50 millisecond comes from the Sonnet SDH days. So there was APS in Sonnet SDH, automatic protection switching, which would provide in a ring topology 50 millisecond convergence time, actually fast reroute time, let's say, because you have another physical link, but APS was the hardware. What we are doing here, we are doing the convergence in the layer 3 by doing some changes in the layer 3. Don't forget, Sonnet SDH APS was providing 50 milliseconds, and it's like a norm or target, let's say, but most of the applications in the service provider and enterprises might be working well with the 150 milliseconds. Either if it's HD video or voice traffic, they are okay with that. though some providers might be looking for 50 milliseconds, and as you can see, their timers will provide us, especially in the core failure case. He just detected the failure within maximum 45 millisecond. Detection is taking the most amount of time, by the way, in the convergence steps. Okay, don't forget, we will see SPF, etc. These are nothing in this today modern CPUs. RIP-FIB update, it depends on the number of prefixes mostly. Again, hardware, if it's powerful, RIP-FIB update will take a lot of time. If you are doing summarization, etc., we are dealing with the less amount of prefix. That's why also this RIP-FIB update, control plane and data plane update will be much faster than a couple milliseconds we are talking about here. 50 milliseconds can be achieved, and we will now continue talking about the timers and the protocols. Mohamed, I still see the same slide.
Yeah, I will go to the next slide. But yeah, what you explained is perfectly right. And yes, the number 50 milliseconds is just inherited, but some of the service providers I worked with recently, they understand that application can even cope for up to 1 second delay, even some mobile traffic. So you don't need to stick to the 50 millisecond, which we inherited from the optical and SDH delay, but it depends on the application and the SLA you sign with your end customers. Let's talk about something which would apply to the LSP and SPF. What we call it is throttling algorithm, which I try to explain it here in a small drawing, that what we are trying to do in order to make sure we have a trade-off between how fast and stable the network will react. So in case if I notice there is or detect a failure, shall I start working immediately, send this to my neighbor and start working on the SPF to find another path, or shall I try to do some changes? So here, as you can see, as a backup algorithm, we decided, as example, if failure happened, that wait 50 milliseconds and do the first run, then for the second run, wait 100 milliseconds, for the third run, do it after 200 milliseconds, and so on, till you reach the maximum, which is 5 seconds, as example. By doing this, you are very fast in reacting to the first failure. Okay, some people even for the first failure you will make it 1 millisecond, and the second 50, and so on. And at the same time, you will make the network stable. You are not wasting resources. That if the link is flapping every few milliseconds or every few seconds, you don't need to keep running the SPF, and this may lead to a lot of micro loops and some packet drops. So that's why the first failure act very fast, the second failure act a bit slower and start going slower and slower in an exponential way, as Orhan mentioned. To meet why you are doing this kind of algorithm, we are trying to do the right balance between being fast and being stable. So in summary, be fast in the first failure and start to go slower in the next one. And so this is what
protocols generally call that pacing timers, and all protocol, ISS, OSPF, LDP, BGP, etc. What does pacing mean? If I see the event, IBGP, EBGP, by the way, they do the same thing, of course. In IBGP case, we call it minimum route advertisement interval, etc. We wait. Why? Because I might be hearing the same event from multiple paths. Should I immediately run SPF? Or should I immediately generate new LSA, new LSP, and then send? Or a little bit wait and send? Same thing for BGP. Should I immediately run BGP best path selection to find the best path and then advertise that best path? There is a pacing timer. We are waiting. We are basically arranging these timers to stabilize. Yes, of course, we will reduce maybe if the application requirement is that. But while reducing, we need to make sure that we are not increasing our CPU and memory utilization, etc., etc. So right balance means that stable as well as fast. And we will have the balance based on what? Based on our network, based on our rate of change, based on our hardware, based on our connectivity, is it full mesh, etc. So based on many things here, this balance, these timers change, many things change. Depends on your network. That's why we say it depends on your network, because your network hardware is different. Your network's flap rate is different. So the pressure to control plane, what you put, what I put might be different, right? So yeah, let's continue on. This prefix priority, I think we are talking about.
Yeah, the last one for ISIS is the prefix priority. As Orhan mentioned, this will give you a couple of few nanoseconds, even sometimes very less milliseconds. That, as example, if you have in your ISIS, let's say, couple of thousand of route, 4,000, 5,000 route, most of them are point-to-point and management and so on, and you have maybe around less than 10 or 20% of these prefixes for loopback, which is the most critical prefix to do. What you can do is you try to mark these critical routes for the loopbacks as a high priority, and all the other routes you can mark it as a medium and low. So in case once the ISIS found another alternate path and it's need to start updating the FIB with the right next hop and the new next hop, it will start with these high priority prefix first. So this will give them few nanosecond and maybe up to a couple of millisecond better convergence, because once you install this loopback, you will be able to establish the LSP and be able to carry the traffic which was labeled in our case.
That's important, this prefix priority. Generally, we call this step as golden prefixes. So those, as Mohamed said, like for the IPv4/32s, of those loopbacks, etc., and the top-level DNS, those kind of things. We have lots of point-to-point interface or infrastructure interfaces, generally also we call it, between two routers. You assign IP address to that interface between the routers. You don't use that interface almost for any reason. You don't use it for SPF calculation. You don't use it for network monitoring, etc. You put that IP address. In fact, in ISAs, you don't have to put at all. You don't have to assign any IP address on the interface for the point-to-point interface. So, but still you are carrying in linked state database, you are still carrying and placing them in a FIB update, so they delay the convergence time. What Mohamed said, we put later. In fact, some people are, even service providers, are removing those infrastructure prefixes from IGP at all. How? With ISAS, it is called advertise passive only. With OSPF, it's called prefix suppression. So they remove it completely, point-to-point addresses. So golden prefixes, so which mean which prefixes will be prioritized, loopbacks, DNSs, etc. Generally they put, and then for the point-to-point infrastructure address, either you place them in a FIB after those golden prefixes, or completely you remove by doing advertise passive only in ISAS or prefix suppression in OSPF. Okay, so we are going well. BGP, what did you do? BGP.
Yeah. BGP, I want just to ask first, does anybody here still believe that BGP is a slow converged protocol? Does it converge in minutes?
Yeah, in control plane, it might be very slow, depends on many things, but yes, you will talk about data plane, you did something, it seems.
Yeah. So I mean, one of the things which make it very slow, it was a huge hello timer, sometimes 60 seconds and up to 3 minutes to converge. And we have this scanner that every 1 minute I just run to see if my neighbor is up and running. So in order to improve BGP, there was a lot of event-driven and a lot of features introduced to BGP, which make it much more faster. Specifically, we have next hop tracking to track your EBGP neighbor, and once you see the link failed, you just flush all the NLRI that you learned from this neighbor. We have fast external failover. We have some enhancement to the scanner idea was deleted, was removed completely from BGP. So I don't wait every minute to go and check my neighbor and check my routing table and this update. I just wait when my neighbor fails, I just react immediately. So all of these actually improved the BGP a lot. And I saw in some cases with not for BGP, I mean like not IP version 4 for the full routing table, but for some customers, and for MBPGP with some specific business customer, we were able to converge in around a second for BGP between the PE and router filter. So this is a very good improvement for BGP. A second point I want to highlight, which some people they are not really, they are either neglected or they are not aware of it. BGP is working on the TCP. It's a protocol number 172. So
79.
BGP consider an application, an application using TCP. So in order to enhance BGP, you need somehow to start working on enhancing your TCP, specifically in the devices where you have a lot of peering, like the router reflector. So how to enhance the TCP window slicing to give it the maximum number, as you can see here in the table, 65,000. You need to start, now it's enabled in most of the iOS XR and Cisco, the selective ACK. You don't need to ACK the last message you received. You just send back to the sender which packet you didn't get, and it will just send this packet, not repeat everything from the one you lost. And a lot of enhancement to TCP, which will improve the BGP. So just to summarize, some feature like next hop tracking, fast external failover, allow the BGP to converge very fast and to act as an event-driven, not like only waiting for the BGP neighborship to expire and then remove the routing information. Also, some enhancement to TCP in addition to the thing which we did in ISIS, like also rely on DFD. DFD over bundle for BGP is supported in most of the new devices. MSR, and also maybe for within your network, because you know that minimum advertisement routing interval it's different by default between EBGP and IBGP. So within your network for the neighborship with the router reflector is also recommended to configure it to 0 because some of the devices this default is 30 milliseconds, 60 milliseconds, and so on.
Okay, let me
Back to you.
let me add a couple things here. For the what I see, couple things there to talk. Next stop tracking is a working mechanism. Mohamed mentioned about BGP scanner. BGP scanner is a process which basically before next stop tracking also was there to find for the BGP to find if there is a next stop failure or not. Runs every 60 seconds, and this is for every implementation same. Cisco, Juniper, etc. So, but with the next stop tracking, it's similar to BFT. When I see NHT, it's similar to BFT. From if you would give analogy, why BFT? All the protocols register to the BFT, and if BFT session goes down, protocols are informed. So that's why you don't have to tune if you have IGP, BGP, MPLS, lag, etc. in your network. Aggressive timers on the control plane. No, you just set up the BFT session and BFT light data plane offload mechanism for fast failure detection. Then basically BFT inform them. BFT inform its clients. Next stop tracking is the same thing. Next stop tracking, what happens with the NHT is when there is a, let's say, next stop failure, and this next stop is carried via IGP, your ISAS. ISAS informs when you have next stop tracking. ISAS informs that in case of next stop failure about that next stop failure to BGP process. So IGP is carrying your next stop, right? So either loopback interface or maybe outgoing interface. That interface is carried via IGP, and when there is a failure, IGP inform the BGP with the next stop tracking. So that's why we also say BGP convergence. Even if you do BGP prefix independent convergence, BGP convergence depends on the IGP convergence. That's why we say, because next stop tracking is important. Another thing, I see IGP wait for BGP, and I want to ask, did you do anything with the overload bit here in ISAS?
Yes, actually, we no, in this specific service provider, no, we didn't configure overload bit. For other projects, yes, but for this one specifically, no.
IGP wait for BGP. What did you do there for that?
Yeah, I mean here we configure IGP wait for BGP, but we didn't configure overload bit for ISIS.
So when basically when there is a failure, and if on the node running IGP as well as BGP, which should be edge node anyway, because in the core you have MPLS LDP, I think here, because IGP LDP Sync you are saying, when you have LDP in the core, you don't run BGP in the core. So on the edge it seems IGP wait for BGP. What does it mean in case of that device fails, the router fails, and come back? IGP, before declaring that I can be used as a transit device, I can be used to pass the traffic, BGP needs to be converged. When BGP is converged, BGP, there are many messages, especially BGP, when it sees BGP end of rip marker message. End of rip marker mean between the BGP neighbors that I received all the prefixes from you. Then BGP this time informs IGP and it says, okay, now you can advertise regular metric, regular cost. So then it also joins to ISIS and then receive the traffic. IGP wait for BGP in OSPF. Also it's there as a feature in ISIS, of course it's there as well. Basically why we are doing, in case of failure, we don't want to black hole the traffic. That's the reason. Whatever implementation, which configuration command, etc., we don't share, of course, those things. Why we are doing, what it would provide for us. Do you need this one in enterprise? There are many questions, huh? But generally no. And what it provides, black hole avoidance, basically. I seen there LDP Session Protection as well as IGP LDP synchronization feature in MPLS. Exactly same reason. We want to avoid black holing in case of failure. So protocols are synchronizing. IGP synchronized with BGP. IGP follows BGP. Now IGP will synchronize with LDP as well. IGP will wait LDP before advertising the regular metric.
Exactly. Yes, thank you, Orhan. Actually, you nailed it. Exactly. So this is summarized BGP. Actually, I saw, while you were talking, I saw a question on the chat about BGP pick. So yes, in this project, there was BGP pick, but I saw that there will be too many technologies to discuss today. So as Orhan mentioned, maybe we will have another session talking about another implementation where we have segment routing with TI-LFA, and we were having BGP on top of segment routing, and we were using the BGP pick. I believe it will be a very interesting one, so we will talk about it in the upcoming session. Just finally, to wrap up, also for MPLS itself, we were using LDP, and as you can see, some of the feature here is just more like a control feature. It's not actually a fast convergence feature, but it's something like a good practice. So usually, if you have your network, and LDP by default will assign a label to every prefix in the IGP. So as I mentioned, if ISIS has 4,000 routes, LDP will assign label for all these 4,000 routes. This is not good. Even when LDP will convert 4,000 label and prefix, it will take more time than if it's you're only converging 200 or 300 labels. So that's why don't put yourself in a problem, then try to solve it. Put a good design. So from the first day, try to control which the label which you will assign, which prefix you will assign label for it, and stick only to the loopback /32, and also apply which label you need to advertise and to receive. So some implementation like Cisco, you have maybe some allocate label and advertise label. Some other implementation in Juniper, you have even the more control and assign, send, receive, and so on. So this is one point you need to consider. Also, as Orhan mentioned, PFD, we can use it. Also for LDP, you need to sync up with IGP because you rely on IGP, okay? And one of the last point, if you have, as example, if you have your device and you have multiple links, so you may configure something like LDP Session Protection, because you run maybe the LDP between the loopbacks, and to reach this loopback, you are using this interface. In case of this interface fail, you can check another interface before declaring this LDP down. So LDP will check with underlying protocol how to reach my next hop for my neighbor LDP, and in case of failure, will not declare the session down immediately, but will wait for any protected session, protected path to reach this neighbor. And the last point, we have something called LDP backoff, which actually implemented. I didn't see it a lot, but for this service provider, we implemented. If you have also two neighbors, and let's say there's a link, one link, and this link is unstable, so it keeps flapping up and down, up and down. So in order to avoid that each time the link flap, these two LDP neighbors will try to establish the session and then tear it down. Maybe after couple of times, you will inform these two neighbors, just wait 5 to 10 seconds before trying again to establish the session. This feature will add to the stability of your network, which, as I mentioned, sorry for that, it was mainly a service provider with most of the traffic was carried over label switches path, label switched path, LSP, and LDP is actually a key protocol to establish this LSP.
For the left example, LDP Session Protection, if that top path goes down, and if you are basically enabling, let's say, the LDP session between your loopbacks, anyway, those loopbacks can be reachable via bottom path, which is already up and running. Top just failed, so that's why you don't bring the LDP session down with the LDP session protection. LDP IGP sync though, LDP session will go down, but the devices will continue, routers will continue to keep the label assignments, because when it come back, IGP will converge faster than LDP, and IGP will immediately update that you can use me as a transit router, but without label, you would black hole the traffic again. So in order to prevent that, these are different approaches, LDP Session Protection and LDP IGP Sync, though in the same network, both of them could be used. Probably I wouldn't enable both of them at the same time, though. So LDP Session Protection and LDP IGP Sync are used for black hole avoidance, same as IGP BGP wait. IGP wait for BGP. Also, I asked overload bit. So basically, IGP BGP synchronization, you can call it. They didn't enable on this network. So these are so good so far. There was another question on behalf of Mohamed. I can answer, though I don't know this network. Did you enable AdPet? He says no, they wouldn't, because in this network they have MPLS, and if they would want to get the benefit what you would get from AdPet, they will deploy unique RD per VRF per PE. Though it doesn't mean AdPet doesn't work on top of MPLS network. Of course it does, but you don't just need it. Just assign different unique RD for the VRFs, for the VPN customer on different PEs. That's it. So you can get the same advantages like advertising multiple paths, or if you want to do multi-pathing, or if you want to avoid suboptimal routing, or if you want to avoid med-oscillation problems, etc., what you would get from the AdPet. Also, NHT is by default on correct. Yes, that's correct. Do you think session protection can sometimes cause false positive as it's established targeted LDP? Good question. Might be, yes. So, any other things that we will talk?
I think that's it. I like to, as usual, let me see. Can you see my screen?
Yep.
Well, just to sum up, some lesson learned. So there was a question that most of the service providers will try to convert within 50 milliseconds. It's just something like legacy, which we inherited. So don't go and implement it without studying and analyzing the real application requirement and the SLA. So even some service provider, and they have mobile customer, and they are actually their role is to converge maybe within second or 200 millisecond and so on. So design based on the requirements. So this is very important point. The second point, how fast is fast? So what you consider very fast convergence, maybe for other networks is not fast at all. So that's why you need also to agree with all the stakeholders, with the application owners, with the different business unit within the service provider, the internet business unit, the MPLS, I mean the VPN and so on, defining how fast is this fast convergence for you. As I mentioned, in some situation, if you are having interoperability with other vendor or other, even within the same vendor, but different hardware or different capabilities, you need to choose the minimum common denominator. Sorry.
Denominator, yeah, it's hard to say.
I'm a bit tired. It's almost 10 p.m. here. So as I mentioned, if you have one device support 50 millisecond or 15 millisecond as a BFD keep alive, but the other device only support up to 100 millisecond, you need to go with the lowest. Even if you configure one with them was 15, we will negotiate and decide which one is the best. But from design perspective, consider this limitation into your design. And somehow not related to fast convergence, but related to the overall design as a whole. When you consider your redundancy and resiliency, and in case of failure, you need to plan. In case of failure, will this affect your traffic? Will it be deterministic? Are you aware of what will happen in case of failure? As example, the traffic will go to another country or another state, affecting your international links. So all this you need to also include while thinking about fast convergence. Once again, I want to thank you all and thank Orhan for this initiative. Actually, it's very great. It's very good from him and to help the community. And thank you again, Orhan, and everyone.
Thank you for joining again, Mohamed. Guys, hopefully it was nice and useful. We will continue the sessions with Mohamed, with the other industry experts as well. Yesterday, I published the IXP video, Internet Exchange Point Real Life. Today, we just recorded the service provider, not this time Internet Exchange Point, but this time Internet Service Provider Real Life Design. It's we look at from convergence aspect. We talked about some timers from IGP point of view, BGP, MPLS, multiple layers, what we did, etc. defined here. It was I think nice and not that lengthy session. So hopefully you start from the beginning and finish till end. If you have any question below this video, please in the comment section you can ask. We will be answering your questions. If you like the video, if you found it useful, please like it, comment it, and don't forget to subscribe to the channel as well. We will continue the sessions. If you just like it and if you find it useful, how we will understand if you find it useful, just liking or commenting. If really this service provider real life design stuff, you think that there are so many things already there, people are already talking service provider real life design, etc., or somehow if you are not interested, don't. But if you are interested, like it, so we can continue with the Mohamed and other people also. I can understand the service provider design, what people are interested with. We can continue. So here I am seeing lots of feedback, but I want to see them when we published on YouTube, especially, right? There, hopefully you also write yes, because we will be monitoring all those comments, etc. So if it's really useful, we should continue in this way. We say, okay, ISP, they are interested. IXP, they are interested. Data center, they are interested. We can understand what are their interests really and try to be more useful on that space. That's the whole reason. We were planning enterprises as well with Mohamed, but we said, okay, let's start with the service provider first and let's see what will happen. Basically, put your comment, like the video, and subscribe for getting a notification. You can reach us both. We are using LinkedIn, Mohamed Radwan. You can see our names here, by the way, Orhan Ergun. You can follow us also on LinkedIn, guys. And thanks everyone for joining. Thank you, Mohamed, again.
Thanks, friends.
Okay.
And have a good day. Stay safe.
You too. You too. Stay safe, everyone. Bye for now.
Bye.